Okay. So hi, I'm Lin Clark, and I make code cartoons. And I am joined today by Till Schneidereit. We work on the developer technologies team at Mozilla. So if you aren't familiar with what our team does, we work on the Rust core language. We also work on WebAssembly tooling, and we work on the Rust to WebAssembly toolchain. And if you aren't familiar with WebAssembly, it started as a way to run programming languages other than JavaScript on the web. So these are languages like C, C++, and Rust. But our team is actually pioneering a lot of work on outside the browser WebAssembly use cases. And this past spring, we actually announced an initiative that's going to make these outside the browser use cases a lot easier. And there's been a huge uptick in interest since then, with people like the co-founder of Docker, Solomon Hykes, saying that if this tech had been around 10 years ago, they wouldn't have needed to create Docker. So in this talk, we're going to explain why people are actually excited about this. So first, we'll talk about why you want to run WebAssembly outside of the browser, and then we'll talk about how we got to the place where you could even think about running WebAssembly outside of the browser, and then we'll talk about the future of WebAssembly outside the browser and the foundations that we need to put in place to make this future possible. Now, most of the time, when Till and I are talking about the future of WebAssembly, we use this diagram of upcoming features. It's from a post that we wrote about WebAssembly's post-MVP future with Luke Wagner. And you can find this on Mozilla's Hacks blog if you want to learn more about this. So we go through all of the features that are still needed inside the browser to enable all of the different use cases there. And then we get to outside of the browser. And then sometimes people get confused when we start talking about outside of the browser. Because isn't the browser what you use to view the web? And isn't that right in the name, WebAssembly? But the truth is that technologies like HTML and CSS and JavaScript, those are only part of what makes the web. You know, they're the visible part. They're what you use to make user interfaces, so they are the most obvious part of the web. But there's another really important part of the web which has properties that aren't as visible. And that's the link. So the innovation of this link is that I can link to your page without having to put that link in a central registry or ask you or even know who you are. It's this ease of linking that made it possible for us to create these global communities with people that we don't even know. But there are two problems here that we haven't addressed just with this link. The first one is, you go to visit this site and it delivers some code to you. How does it know what kind of code it should deliver to you? Because of course, if you're running on a device, if you're running on Mac, you need a different kind of machine code than you would if you're running on Windows. Does a website need a different version of the code for every different device? No. So instead, the site has one version of the code, the source code, and that's what's delivered to the user. And it's translated to the machine code on the user's device. And of course, the name for this concept is portability. So with it, websites don't need to know what kind of device you're running. But that brings us to the second problem. If you don't know these people whose web pages you're loading, how do you know what kind of code they're giving to you? It could be trying to take over your system. So doesn't this vision of the web, running code from anybody whose link you follow, mean that you have to blindly trust whoever's on the web? This is where the other key concept comes in. So this is the security model. And basically, the browser puts this code into a sandbox, and it puts a few toys into that sandbox that aren't too dangerous, but leaves the dangerous things outside of the sandbox. So the utility of the link is based on these two things. Portability, being able to deliver the same source code to any device and just have it run. And the sandbox, the security model that allows you to run that code without worrying about whether or not it's putting your machine at risk. So what difference does it make to think about the web in this way? Well, it changes how you think about WebAssembly. You can think about WebAssembly as just another tool in the browser's toolbox, which it is, but it's not just that. WebAssembly also gives us a way to take these other two capabilities of the web, the portability and the security model, and bring them to other use cases that need them too. So we can expand the web past the boundaries of the browser. So what kinds of outside the browser use cases, what kinds of problems can we solve by doing this? Let's walk through one concrete example. So for this example, I want to talk about Node. With Node, it's possible to run JavaScript on servers and other devices that don't have a browser. So that gives us some portability. But you need native modules in a lot of cases. either because the native code performs better or because you already have a code base in C or C++ and you want to reuse that. But native modules aren't portable. They need to be compiled specifically for the device they're going to be running on. And we're also still missing security. Node could have taken that sandbox from the browser, but Node made the design decision early on that JavaScript modules were going to have full access to system APIs. So JS modules can do things like write and read files. These capabilities, things like full direct file access, are those dangerous toys that we don't put into the browser sandbox. Now, these capabilities, they do actually make a certain amount of sense for the kinds of use cases that Node's meant for. Even though they're dangerous, there's still a certain amount of sense there. The thing I want to make clear here, though, is that Node made a choice. And really, it's that Node had a choice to make. For JS modules, it could have gone with a sandbox-style approach. But for native modules, Node has less of a choice, because it's actually pretty hard to sandbox native code. This choice that Node made, it means that if you're running a Node application, you basically have to say, I trust this code. I trust that it's not going to try and take over my system. This is where WebAssembly can help Node. If native modules were compiled to WebAssembly instead of directly to native code, then these modules would be portable and they would be sandboxed by default. But they would still have the performance that you have from native modules, native Node modules. The only problem with this vision, though, is that WebAssembly doesn't have direct access to the system's resources. That's part of the security. That's the sandbox. So we'd need to pass in functions that the WebAssembly module could call to do this kind of interaction with the system's resources. So for Node, that would probably include a lot of the functionality that's in C standard library and POSIX. To make this happen, the Node core folks would need to figure out what API they want to use for these functions. But wouldn't it be nice if that were actually something standard? Not something that was constrained just to Node, but something that could be used across other runtimes and other use cases too. Now, what I've said here in other versions of this talk is a POSIX for WebAssembly, if you will. A POSIX, a portable WebAssembly system interface. It was the goofy name that we gave to this idea, and I kept it in the talk because I always got like a little bit of a chuckle. But the idea itself wasn't a joke. And here I would talk about how, if this system interface, this POSIX, were designed in the right way, you could even implement the same API, but in a different way for the web. So that's what I used to say here. But I don't have to talk about this in what-if terms anymore. Because we recently started a subgroup of the WebAssembly community group to standardize the system interface. And we seeded it with a proposal for how this should work. The name that we actually gave to this system interface was WASI, the WebAssembly system interface. Now, WASI won't be part of the WebAssembly spec, and there may be WebAssembly hosts that don't make these system calls available. That's totally fine. But for those platforms that could make use of this system interface, there will be a unified API for calling these functions no matter which platform you're running on. And this will make writing those universal modules, ones that run on both the web and other runtimes like Node and whatever other runtimes implement this, so much easier. This opens all sorts of new use cases for WebAssembly, and I'm going to let Till explain more about those.
Thanks, Lin. Lin is right. WASI opens up a lot of use cases across a wide array of different domains. One of them is the domain of CDNs, serverless, and edge compute. The Fastly CDN, for example, serves a surprisingly large fraction of the internet's traffic. And they're doing this with a large network of machines that are installed all over the world to be as close to the client as possible. And they are moving from just serving static files using their CDN to running their customers' code on potentially every single request. And they are doing it in a way that doesn't require them to install, say, 10 times as many machines in this network as they have now. which is really what they would need to do with more traditional server architectures, where you would use a container to run untrusted code or other heavyweight mechanisms. Instead, WebAssembly gives them the sandboxing that they need at the scale and at the speed that they need. People are also working on building blockchain platforms with WebAssembly. There are, at last count, a dozen or more of those. There's interest in the IoT space. Just last week, Lin and I talked to people from ARM who are experimenting with this, and we know that Intel are also experimenting with using WebAssembly to make different devices compatible. And people are writing CLI tools, portable CLI tools with WebAssembly. Among other use cases, there's also, or in general, what use cases have in common very often is that they need this lightweight sandboxing and portability, where, for example, a game engine could run the game logic in the engine without, where logic bugs in the game logic shouldn't imperil the stability of the overall code. And we are doing something very similar in Firefox, where we are taking entire libraries and moving them into a lightweight sandbox in the same process to ensure that the library can't access the entire process's memory. All of these use cases have in common that sandboxing is important to them, and for many of them, portability is highly important. But I want to highlight some additional important commonalities here. For example, how do things like network access work or reading files? The way to do these things should ideally stay the same across this wide array of different use cases, and also across the different runtimes that you would use to run this code. In today's runtimes for WebAssembly, Node and the browser, JavaScript is used to talk to the outside world. If you're running in the browser, you use fetch to load files from the server. And this is all standardized across different browsers, so you can rely on it working in a predictable way. In Node, you use fs.readFile to, well, read a file. And you can also rely on this, but for a different reason. All these Node APIs, they are not standardized. But you can rely on it because there is just a single implementation that you're going to use, and that is Node, and it's built in modules, it's built in library itself. Because Node is a de facto standard, you can rely on the behavior of its APIs. With WebAssembly, ideally, we'll have the same situation where you can rely on the APIs, but it should otherwise be more similar to the browser use case. So we don't want to achieve reliability and portability across all these use cases by having a single dominant runtime, and there really not being any space for alternative runtimes that are really truly tailored for use cases. Instead, as Lin said, we are working towards a standardized runtime environment, where for all the functions that a runtime provides, you can rely on its behavior, on the behavior of the APIs it provides. And Lin mentioned POSIX as a sort of superficially obvious choice for doing this. And we could have said, let's do POSIX, let's do, what did you call it, a POSIX, and just be done with it. Other people have done the design work. Unfortunately, that would have eliminated one of WebAssembly's big security advantages, which is this tight sandboxing. Lin talked about how Node had a choice to make, at least for JS modules. A choice between keeping the sandboxing that JavaScript has in the browser, or providing developers ergonomic, efficient ways to talk to the outside world. And we now have a very similar choice to make. Do we keep this sandboxing, or do we provide developers with traditional established ways to talk to the outside world? We believe that we should keep the sandboxing, and that we should keep something that leads to better security, to better control, and to better auditability. And that last point is really important. You should not need to carefully review every single line of an application's code to see what it could possibly do to your system. NPM taught us that that clearly does not scale. Instead, what you should be able to do is essentially look at the label and see these are the capabilities this application needs to be able to operate. And then you can make an informed decision. Say, does it need to be able to access files in a single directory and write output to a single file? That's probably fine. Does it need to access every single file that your user account has access to on your hard drive and then send random things off to the internet? Maybe be more careful with that one. With POSIX, doing something like this is incredibly hard, and it requires a lot of help from the operating system. And naturally, this works differently across different operating systems. So at the very least, there goes your portability. Solid portable sandboxing is really incredibly hard. And back when Node was created, nobody had figured out how to take the learnings from academia and really apply them to the to industry, to make them work at scale with high productivity for a general developer audience. But this has changed. Better designs exist, and they have been proven out. Google's Fuchsia is an example, Capsicum is an example, and Lin will tell you more about WASI in a moment. Before that, I want to talk a bit about how we got to this point. How we put the foundations in place to even be able to talk about bringing WebAssembly to outside the browser. So, how did WebAssembly itself come to be? The inspiration started with Emscripten, all the way back in 2011. Emscripten allowed developers to take existing C and C++ code bases and compile them to JavaScript and run them in the browser. That JavaScript wasn't fast, and it also looked kind of funny. See, JavaScript is untyped, or is dynamically typed, so every parameter can have any type of value whatsoever. But C and C++ need reliable types. They need to ensure that an integer, if a field that is expected to hold an integer, actually only does hold an integer. So the Emscripten code, the JavaScript code that Emscripten emitted, used Boolean operators to enforce this, to enforce that every local really only contained integers. It was the insight of Luke Wagner, who's here today, and who then was one of the engineers on our SpiderMonkey engine in Firefox, that there's a pattern here that we can use, where we can use the reliability of this effectively typed system to create much better code much faster. So he added effectively an annotation, use asm, as a string that normally an engine that didn't know anything about it didn't do anything. But that told an engine that knew about it, the code here will behave in a very predictable way. It'll use these type annotations, this type system, in an agreed upon way. And during parsing, it would validate this. It obviously couldn't trust just this assertion. So it would validate that, yes, this is actually kept. And all the while, during parsing, immediately also generate highly optimized machine code instead of letting this JavaScript code go through the normal process of compiling to a bytecode, running in an interpreter, then at some point going through different tiers of JIT compilation for hard code. That was ASM.js, a highly optimizable subset of JavaScript. With that, C and C++ were able to run in the browser at pretty respectable speed. It, in fact, went so well that Epic were able to take their Unreal engine and port it to the web. And that is where we got this famous Citadel demo from that some of you might have seen. This is a AAA, back then AAA high-performance game engine running a really complicated 3D scene with dynamic lighting and all the things that were state-of-the-art back then, with 60 frames per second in the browser. Absolutely unheard of before then. ASM.js demonstrated the viability of this approach, the viability of running compiled code with security within the sandbox with acceptable performance. But is compiling to a subset of JavaScript really the best we can do? Well, no. But it did give us a good baseline. And based on that, developers from the major browser vendors came together to create a whole new way of running native code in the sandbox on the web. And this is how we got to the announcement of WebAssembly in 2015. And what you see with WebAssembly today in the community around WebAssembly was sparked by this initial announcement in 2015. That announcement focused on the browser. But even then, they knew two things. One, that this was just the beginning, and two, that WebAssembly would not be confined to the browser, the name notwithstanding. They also knew that it wouldn't just be C and C++. And by now, dozens of languages compile to WebAssembly. In 2016, our Rust team started releasing initial versions of the compiler that could target WebAssembly. And today, Rust is widely seen as having state-of-the-art support for compiling to WebAssembly and for interoperating with JavaScript. I'll get back to that last point in a moment. 2016 is also when we first started seeing people play around with WebAssembly outside of the browser. This is when we saw the WAVM runtime project start that was based on LLVM. I know this was a year before even stable support shipped in browsers. So a lot of things were still missing. This is still very much an emergent ecosystem. And for the most part, the focus did stay on the browser. And in 2017, WebAssembly reached its MVP, its minimum viable product, and was shipped, turned on by default in all the browser engines. And with that, we saw a whole lot of renewed interest pour into WebAssembly. And we started seeing tools emerge that were really specifically focused on WebAssembly. Mozilla contributed to this with our Brainlift code generator that is highly specialized for WebAssembly. It was started by a former LLVM core team member and is today led by another LLVM core team member, Dan Goman, who is also the creator of the LLVM backend for WebAssembly. I talked about Rust earlier. One thing that the Rust team realized is that they could apply some of the more modern features of Rust as a language to make it easier to interoperate with the outside world, with JavaScript in this case. And they really doubled down on this. They created a working group led by Nick Fitzgerald around building best-in-class WebAssembly support. And using features like procedural macros, they created something that allows you to interoperate with JavaScript using high-level constructs on both sides. And actually, a lot of this work now informs work in the standardization process around creating high-level bindings across languages and to talk between the host environment and content running in WebAssembly. This is also where we started seeing an inflection point. More and more people were starting to experiment with WebAssembly outside of the browser. But there was a problem. We were seeing the beginnings of something that we thought was dangerous. In fact, things were starting to play out in very similar ways to what had happened 10 years earlier in JavaScript. For JavaScript, we are now currently, as a community, doing the work to dig ourselves out of the hole we are finding ourselves in. When JavaScript was brought outside the web, we left the sandbox behind. And that is why JavaScript code might steal your Bitcoin wallet. And we knew that we couldn't let that happen to WebAssembly. We needed to ensure that we keep our users secure and that we build a new set of secure foundations for the future. In fact, we believe that it is verging on irresponsible to support running WebAssembly in a runtime without strong sandboxing support. So what should these foundations look like? That is where we return to WASI, and I'll let Lin explain.
Thank you, Till. So I'm going to explain at a high level the what, the why, and the who of WASI. And then we can start diving into some of the details of the system interface. So first off, why? Why would you want to run WebAssembly outside of the browser? And we talked a little bit about this already with, the security and the portability. But those aren't the only reasons. Another reason is that WebAssembly is fast. If you want to run code in a safe, portable way, it'd be hard to find something faster. It gives you the ability to run code at near native speeds. And it's not just that the code runs fast. WebAssembly code can also give you fast startup times, and VMs built for WebAssembly can start up more quickly. So for example, Till mentioned Fastly. They're using WebAssembly to handle requests for their serverless platform. And they do this by spinning up a new virtual machine instance on every single request. They can actually instantiate WebAssembly modules in under 60 microseconds. And so for comparison, if you're instantiating a JS module in something like V8, it takes about 5 milliseconds. WebAssembly is also scalable. Going back to this Fastly example, their WebAssembly runtime only requires a few kilobytes of memory overhead, compared to V8, which takes up tens of megabytes. So this means that they can have tens of thousands of simultaneously running programs in the same process, compared to hundreds with V8. So that's why you would want to run WebAssembly outside of the browser. Now let's look at what, and exactly what WASI is. So when I was first talking about WebAssembly, I talked about how it was an assembly language for a conceptual machine, not for an actual physical machine. And this is why it can run across all of these different machine architectures. It's very close to the assembly language that's used by a lot of machines. So the runtime only needs to do a small hop, this small translation from WebAssembly to the actual assembly language for that machine. So, going from this conceptual machine language to the actual machine language. Just as WebAssembly is an assembly language for a conceptual machine, WebAssembly needs a system interface for a conceptual operating system, not for any single operating system. And this way, we can run it across all different kinds of operating systems. And this is what WASI is. It's the system interface for the WebAssembly platform. Now, who's doing the work on this? I mentioned this before. We chartered a subgroup of the WebAssembly CG to work on this. And so if you want to get involved, you have a few options here. You can join the CG and work on the standardization, or you can also start contributing to one of the implementations. We're working on one called Runtime. Fastly has their Lucid one. Or if you have an existing project that you think could use WASI, feel free to get in touch with us. We'd be happy to talk through it with you. So for example, we've been talking about this with the Node folks about how they could possibly use WASI to replace that native module solution that they have with one that's based on WebAssembly modules using WASI. So now that we've covered all of this, let's talk about WASI in more depth. Now, I know this audience is probably a bit more familiar with operating systems concepts than the audiences I often talk to. But I think that sometimes covering the basics is good, even with an audience that is so knowledgeable as you all, because it makes sure that we're all on the same page. So I'm going to be covering a few basics here. Please bear with me. Now, many people talk about languages like C giving you direct access to system resources, but that's not quite true. These languages don't have direct access to do things like open or create files, on most systems at least. Why not? Because these system resources, such as files and memory and network connections, they're too important for the stability and security of the system. If one program unintentionally messes up the resources of another, then it could crash the program. Even worse, if a programmer or user intentionally messes with the resources of another, it could steal sensitive data. So we need a way to control which programs and which users can access which resources. Now, people figured this out pretty early on and came up with a way to provide this kind of control, and that's protection ring security. So with protection ring security, the operating system basically puts the protective barrier around these resources, and that's the kernel. And that's the only thing that gets to do things like create a new file or open a network connection. Now, the user's programs run outside of this kernel in user mode. If a program wants to do anything like open a file, it has to ask the kernel to open the file for it. And this is where the concept of the system call comes in. So when the program needs to ask the kernel to do one of these things, it asks using a system call. And this gives the kernel a chance to figure out who's asking, which user. And then it can see if that user actually has access to this file before it actually opens the file. On most devices, this is the only way that you can access the system's resources through these system calls. And it's the operating system that makes these available, and each operating system chooses which system calls it makes available. But if each operating system has its own system calls, wouldn't you need a different version of the code for each operating system? Fortunately, you don't, because of abstraction. So most languages provide a standard library, and while coding, the programmer doesn't really need to know what system they're targeting. They just use this interface. And then when compiling, the toolchain picks which implementation to use. Does it use the implementation that has Windows APIs, or does it use the implementation that has POSIX APIs? This poses a problem for WebAssembly, though. With WebAssembly, you don't know what kind of operating system you're targeting, even when you're compiling. So you can't use any single operating system interface inside of the WebAssembly implementation of this standard library. So this is what I mentioned before. WebAssembly needs a system interface for a conceptual operating system, not any single operating system. But there are already runtimes that can run WebAssembly outside of the browser, even without having the system interface in place. So how do they do it? Let's take a look at that. The first tool for producing WebAssembly was Emscripten, and it emulates a particular system interface, POSIX, on the web. So this means that the programmer can use functions from libc, because Emscripten created its own implementation of libc. And this implementation splits things in two. So part of it's compiled into a WebAssembly module, and the other part was implemented in JS glue code. So this JS glue then calls into the browser, and the browser calls into the operating system. Most of the early WebAssembly code was compiled with Emscripten. So when people started wanting to run WebAssembly outside of the browser, they started by making this Emscripten compiled code run. So these runtimes needed to create their own implementations for all of those functions that were in the JS glue code. There's a bit of a problem here, though. This interface that was provided by the JS glue code wasn't designed to be a standard or even a public-facing interface at all. because that wasn't the problem that was solving. For example, a function that would be called something like read in an API that was meant for public consumption, the JS glue code instead uses _system3, and the parameters are which and var args. So the first parameter, which, is an integer, which is always the same as the last number in the function name. The second parameter, var args, those are the arguments to use, and it's called var args because there's a variable number of them. But WebAssembly doesn't actually provide a way to pass in a variable number of arguments to a function. So instead, the arguments are passed in via linear memory, so basically via the heap. Now this isn't type safe, and it's slower than it would be if you could pass these in via registers. Now that was fine for Emscripten running in the browser. But now runtimes are treating this as a de facto standard, implementing their own versions of this JS glue code. So they're emulating an internal detail of an emulation layer of POSIX. This means that they're re-implementing choices like passing in arguments as heap values that made sense based on Emscripten's constraints, even though these constraints don't apply in their environments. If we're going to build a WebAssembly ecosystem that lasts for decades, we need solid foundations. So this means that our de facto standard can't be an emulation of an emulation. But which principles should we apply? So this is where we come back to these two, to portability and security, these things that are baked into WebAssembly. We need to maintain these key principles as we move to outside the browser use cases. And as it is, POSIX and Unix's access control security don't get us there. So let's look at where they fall short. And we'll start with portability. So POSIX provides source code portability. That's the P, portable part of it. You can compile the same source code with different versions of libc and get to different target machine. You can target different machines with this. But WebAssembly needs to go a step past this. We need to be able to compile once and run across a whole bunch of different kinds of devices. So we need portable binaries, not just portable source code. This kind of portability makes it so much easier to distribute code to users in different kinds of devices. Now let's look at security. When a line of code asks the operating system to do some input or output, the operating system needs to determine if it's safe to do what the code's asking. Now, operating systems typically handle this with ownership in groups. So for example, the program might ask the operating system to open a file, and it will have the rights of the user who started it. Now, if the user has access to the file, either because they're the owner or because they're in a group that has access, then that program has that access too. This protects users from each other, and that made a lot of sense when these early operating systems were being developed. Systems were often multi-user, and system administrators were controlling what software was being put on there. They could audit what software was being put on the system. So the biggest threat you had was that other users were going to take a peek at your files. But that's changed. Systems today are usually single user, but they're running code that pulls in lots of third-party code of unknown trustworthiness. So now the biggest threat is the code that you yourself are running is going to turn against you. So for example, let's say that you have a library you're using in your application and it gets a new maintainer, which often happens in open source. Now that maintainer may have your best interests at heart, or they may be one of the bad guys. And if they have access to do anything on your system, so for example, open any file in the entire file system and send it over the network, then their code can do a lot of damage. So this is why using these third-party libraries that can talk directly to the operating system can be so dangerous. WebAssembly's way of doing security is different. So the sandboxing means that the code can't talk directly to the operating system. But how can it do anything with the system resources then? The host, which might be a browser or might be a WebAssembly runtime, puts functions in the sandbox for the code to use. And this means that the host can limit what this program can do on a program-by-program basis. It doesn't just let the program act on behalf of the user, calling any system call with the user's full permissions. Now, just having this mechanism for sandboxing doesn't guarantee security. We could still put all of the capabilities into the sandbox, in which case we're no better off than before. But at least giving the option for hosts to secure themselves is a step in the right direction. In any system interface that we design, we need to uphold these two principles. Given these two key principles, what should the design of this WebAssembly system interface be? Well, we're going to be figuring that out through this standardization process, but we kick that process off with a proposal. Create a modular set of standard interfaces, and start with standardizing the most fundamental module, WASI Core. What will be in WASI Core? Well, in our first proposal, we said that WASI Core would contain the basics that all programs need. But this has changed a little bit, and we've whittled it down. I'll talk a little bit more about that later. But fundamentally, the early WASI modules will cover much of the same ground as POSIX. They'll include things such as files and network connections, clocks, and random numbers. And WASI will take a very similar approach to POSIX for many of these things. So for example, it will use POSIX's file-oriented approach, where you have system calls such as open, close, read, and write, and then other things are basically augmentations built on top of that. But these early WASI modules won't cover everything that POSIX does. For example, the process concept doesn't map really clearly onto WebAssembly. And beyond that, it doesn't really make sense to say that every WebAssembly engine needs to support process operations like fork. But we also want to make it possible to standardize fork. So this is where the modular approach comes in. We're going to fill in a number of different modules. And this way we can get good standardization coverage while still allowing niche platforms to use only the parts of WASI that make sense for them. And we're actually making it even more modular than we talked about in the blog post. Now the system calls for all of these things that I was talking about before, random numbers, clocks, and files. They're going to be broken out into their own modules. And this way your runtime can really pick and choose. So an IoT device without a file system could implement the random number and clock sys calls without having to know anything about the file system calls. How will module developers use WASI? Well, languages like Rust will use these WASI functions directly in their standard libraries. So for example, Rust's open is implemented by calling WASI path open when it's compiled to WebAssembly. So this means that module developers don't actually even need to know about WASI. They just use this standard library, and it all gets compiled in for them. Now for C and C++, we've created a WASI sysroot that implements libc in terms of these WASI functions. And we expect compilers like Clang to be ready to interface with the WASI API and complete toolchains like Rust's compiler and then Scripton to use WASI as part of their system implementations. And in fact, Rust already has support because of the amazing Alex Creighton. Now, how does the code actually get access to these functions? Well, the runtime that's running the code passes them in as imports into the WebAssembly module. So this gives us portability, because each host can have their own implementation of the WASI functions specifically written for their platform. So from WebAssembly runtimes like our Wasmtime and Fastly's Lucet to Node and to the browser. All of us can have our own implementations of this. It also gives us sandboxing, because the host can choose which WASI functions to pass in. So which system calls to allow on a program-by-program basis. And this does preserve security, but we can take it even further, because WASI brings in concepts from capability-based security. Traditionally, if code needs to open a file, it calls open with a string, which is the path name. Then the operating system does a check to see if the code has permissions based on the user who started that program. With WASI, if you're calling a function that needs to access a file, you have to pass in a file descriptor, which has permissions attached to it. This could be for the file itself, or it could be for a directory that the file sits inside of. And this way, you can't have code that randomly asks to open etc password. Instead, the code can only operate on the directories that are passed into it. This makes it possible to safely give sandbox code more access to different system calls, because the capabilities of these system calls can be limited. And this happens on a module-by-module basis. By default, a module doesn't have access to any file descriptors. But if code in one module has a file descriptor, it can choose to pass that file descriptor to a function it calls in another module. Or it can create a more limited version of that and then pass that into that other function. So the runtime passes the file descriptors that the application needs into the top-level code, and then those file descriptors get propagated down through the code on an as-needed basis. This gets WebAssembly closer to the principle of least authority, where a module can only access the exact resources it needs to do its job. Now, these concepts come from capability-oriented systems like Cloud API and Capsicum. One problem that these systems have faced is that it's often hard to port code to them. But we think that this problem can be solved. If code already uses system calls like openat or fopen with relative file paths, compiling the code will just work. If code uses open and migrating to the openat style is too much upfront investment, WASI can provide an incremental solution. With libpreopen, you can create a list of file paths that the application legitimately needs access to. And then you can use open, but only with those files. So what's next? Well, we think that this proposal is a good start. It preserves WebAssembly's portability and security and provides a solid foundation for the ecosystem. But there are still some questions that we need to work on as we're standardizing this. And these questions include asynchronous I/O and things like file watching and file locking. We also need a really solid runtime implementing these foundations in the right way. And we're hoping to have something that can serve as the base for many applications and hosts. If you want to see an example of this, you can check out our Untitled project. It's a standalone WebAssembly runtime, and it's intended to be very pluggable so that you can build custom-tailored hosts on top of it. We think it can be the best-in-class runtime for everything from IoT devices to the cloud. And we're looking forward to talking to people who think it can help with their use cases. So please do come find us after this talk if you want to learn more about that. We'd be happy to talk more about it and about your use case. We want to thank our collaborators on developing this talk, Dan Goman, who's the lead developer on WASI and Wasmtime, and Luke Wagner, who's one of WebAssembly's creators and is pushing a lot of the WebAssembly proposals forward. And he's actually here today, so definitely worth chatting with him and picking his brain on this stuff too. So thank you to them, and thank you all for listening.
completion-based approach to async I/O, whereas Linux uses a readiness-based approach. So how are you going to tackle so many vast differences, and gain portability?
So the question is, how are we going to tackle the vast differences between?
Because, for instance, Java tried this. It had the write once, run everywhere, but it doesn't really work in practice. You still have to deal with, platform differences at the end of the day.
Okay. Do you want to tackle that one?
I can give it a try. You're absolutely right that there are a lot of sort of daunting complexities to tackle. The file system one specifically is different for WASI compared to Java and other systems because we don't actually give you access to the file system, and we don't give you a way to just say, well, here's the file system, go wild. And a lot of the issues Java ran into are because it didn't actually keep sandboxing. What we have in WASI is this, Lin talked about libpreopen, and in general that you can only open paths relative to file handles or directory handles you already have. And we have a concept of mapping paths to others. And as long as you do that, as long as you on the content side only talk about sort of the mapped paths, internal paths and it's up to the runtime to map them correctly. You can have different implementations of the runtime of these mapping mechanisms that actually work correctly in the operating system environment you're working in, and you can keep your content portable. But this only works because we are imposing more restrictions than Java does.
Fair enough, but then again, Open, for instance, in Windows will error if you're trying to open an already open file. On Linux, this is not going to happen, and Linux is more than happy to let you, destroy an existing open file. Which means you can corrupt an SQL database while, Postgres is running or SQLite. So how would you be able to, handle all those minor differences?
So I guess the comment is there's an endless list of minor differences. How do we expect to deal with them? By effectively carving out a compatible subset and imposing that as restrictions, because we want to keep effectively deterministic behavior inside the sandbox, and that only works if we don't introduce operating system dependent mechanisms. One thing that is really important in this is we need a wide range of implementations across very different operating systems feeding into the standardization process, and we need implementations to lead the standardization. We can't sort of be a committee that designs a solution and then says, this seems good, now go and implement it. That simply won't work because we will run into these issues all the time. We need implementations for really a wide range, and then identify all the issues that don't actually work and carve out the subset.
I didn't quite hear the question. I don't know if you did.
The question was timing side channel attacks.
Okay, yeah.
And what do we do about them?
Luke, is this something you'd like to talk about? Fortunately, we have the person who both came up with the idea for ASM.js and has also handled our Spectre mitigations in the browser. So,
yeah, I think fundamentally the industry has realized you need a process boundary to provide any sort of timing protection, and even that's not always as strong as we hope it is, but it's getting stronger. So I think fundamentally in WASI we'll have to expose some notion of you have a domain that provides timing protection, and within that domain you can't expect side channel attacks to be isolated, but with that domain that would give you an implementation would implement it with a process, and that would give you some separation between what's on the other side.
So as a follow-up question to that, in the Fastly example, would they have to spawn each of their separate clients as processes and separate?
Great question. So my answer was for kind of like the general purpose where you're running arbitrary code. The other way to do it is to limit what code is able to access. If you only give it access to purely deterministic primitives, that reduces it somewhat. That's not entirely a solution, even that, as strong as that is. So I think they have a number of complicated answers to that. But it's because they're limiting what the workloads are able to do and what's provided to those workloads.
Mm-hmm.
Or phrased differently, what should I have to do if I want to run a WASI module inside of Runtime and use some shared library for like interoperating with my WASI module? How does that work?
So the question is, what's the story around linking and shared libraries?
And I'm assuming you mean a native shared library, like a DLL, not another WASM module that I want to share memory with. Right. Right. So for that one, we have discussed having basically a DL open in WASI, where you, and coming up with what the right abstraction is, but fundamentally you have to like give a file that you want to open as a DLL and which symbol and what signature you're going to call it with. And as soon as you do this, you start to lose a lot of the safety. Like, this is a very powerful capability. But what we said earlier is we're not, fundamentally people want to use WASM to solve the problems they have to solve when they're outside a browser, so we don't have to impose the security sandbox. We just need to give the host the tools so that it can build as much of a security sandbox as it wants to provide on that host, which is something it doesn't necessarily have today with native DLLs. So if there's a full like DL open anything ability, but a more restricted one might be the host says, here, I'm going to give you these DLLs. I've wrapped them with safe signatures, and these are the only ones you're able to DL open. So that might be a more restricted path. And obviously, we haven't figured this all out yet, because that's a pretty hand-wavy answer, but that's roughly this. We know fundamentally we're going to need to be able to wrap a DLL with some sort of WASM signature.
So, correct me if I'm wrong, I'm trying to capture my understanding, but from a technical standpoint, there's nothing that makes WASM specific. Basically, if you could enforce that, you would be a new POSIX, right? If you could enforce POSIX on Microsoft, so technically on Windows and all versions of Linux, 3264 and variants, it would be just as good from a technical standpoint as a replacement for POSIX. And it has nothing to do with that WebAssembly itself. Is that correct?
It's a great question. One aspect that's, oh sure, yes, right. Oh yeah, saying there's nothing really WASM specific about WASI. I guess the one aspect is what's the ABI of this interface, and by being a WebAssembly system interface, all the types used to describe the signature are WASM. And so that it's an abstract ABI. It's not like actually which registers are passed, but it's at the WASM level, it's fixed. So, but that doesn't mean that doesn't imply a whole lot. You could have the other side know that this WASM signature on this machine translates to this native ABI, and then bind against that. So in that respect, yeah, it wouldn't have to be. You could use WASI without WASM if you so chose.
So another abstraction question is a challenge that other virtual machine interfaces, memory models, and loop memory models in particular. How do you think of abstracting over machines as memory model?
And the question was, how do we abstract over the memory model? Now, fortunately, that is not something we're having to solve in WASI. That one's being solved by the WASM CG proper with a very large amount of leveraging existing research into weak memory models. We have Conrad Watts and Andreas Rosberg working closely together, and they have a fully formal axiomatic memory model that's been iterated on. I think they have a paper out or published in some stage of being released. I think it's definitely public already, but yeah, a lot of emphasis on precisely how to define weak memory models. So it's very rocket science, unfortunately. We were hoping for an operational weak memory model. If anyone here is a researcher in that, that would be great to make some progress. We can get away from the axiomatic world.
Thanks to Conrad's work, formal methods have been quite useful for the WebAssembly specification. Do you see application of formal methods to, say, proving some theorems about WASI and like data flow, integrity, any sort of properties around those kind of aspects?
The question was, can we, we've had a lot of success with formal methods applied to WASM core. Could we bring some of that goodness to WASI? I've been thinking about that a little bit. It's a lot harder with WASM. It's constructive. We've defined it all. So we can just give it an operational semantics. With WASI, fundamentally, we're calling out. And if you look at the one place there's a big hole in WASM's operational semantics is when you call a host function. We say anything happens. All that has to, we have this very hand-wavy constraint of what happens when we resume from calling out to the host. Fundamentally, WASI is sort of in that category. It can say, well, these, here's kind of like the weak memory model, here's some ordering happens before relationships and other things that have to apply, but it's open-ended. What might be more interesting if we grow our WASM standardization over time to start to talk about a container where we can constructively define what's a file because it's inside of the universe that we're specifying. If we could make define our own notion of file, then we could actually say more about them because we're defining what they are in the first place, as opposed to being like an abstract interface between some host thing that we don't know that much about it. So that's farther away. Do you have that?
So additionally, the modular approach might be interesting here. We're starting out with POSIX-like APIs, which have properties that make them quite hard to reason about. But it's clear, Lin had on the slide something about sensors, for example, being, so more higher level use case specific APIs could be in there. But nothing prevents us from defining APIs that would effectively, if you choose to use them, replace a lot of the POSIX-like APIs with ones that have more interesting properties that allow you to have certain amounts of guarantees about them and reason about them in more interesting ways. So we could at least improve on the situation even while having channels to the outside world that destroy this entirely constructive picture we have inside WebAssembly.
Any other questions?
I love your slides. Is that a question?
All right, well, let's thank the speakers.